Yes, we do.
Okay. Okay, so thank you. Today exercises will be about partial derivatives, and we were already computing last week some derivatives in order to remind to the rules, the principal rules of differentiation of functions, and I will I will share my screen soon. We did compute some derivatives of first of one variable functions, and we began to compute some domains of two variables functions, and I'm sharing the screen. Okay, so you should see my screen in order to okay. So in order to compute partial derivatives, we should be able to compute, of course, derivatives of one one variable function. I forgot that maybe you need to, I don't know if we are recording, but maybe yes, I think, because I don't have, wait a minute. Now, okay, so I'm recording these exercises of today. Okay, without a transcription. Okay, so let's begin with some easy two variable functions. For instance, let's put some title. Partial derivatives. Okay. Okay, so we'll begin directly with some examples. For instance, f of x and y equals x squared plus e to the power of 2y. Okay, or you can find z equals x squared plus e to the 2y. Okay. So, what are the partial derivatives? The partial derivatives are the derivatives with respect to one or the other variable. For instance, you should compute everything that you are differentiating. You can write this way, I'm sorry, dz over dx, or you can write the f of x and y with respect to the variable x, and that means that is the derivative with respect to x of the whole function, but everywhere in every everywhere there is this variable we should differentiate. Everything else is considered as a constant. So that means that we differentiate x squared, it is 2x, but differentiating with respect to x, this term of the function means that it is considered as a constant, and so the derivative is 0. So what remains is 2x. The same we can compute for the function with respect to the variable y. Of course, we have as many partial derivatives as many variables there are, and that is the derivative of the whole function with respect to y. In this case, we derive only the second term of the function, because the first one depends only on x. That means it can be seen as a constant, so the derivative of a constant will be 0. That means that we compute the derivative of the exponential function, that is the derivative of the argument, times the exponential function as it is. And this is the first partial derivative. The name of the vector that represents all the partial derivatives, the name is gradient. So we can write this symbol. This is a nabla. Nabla of f of x and y means the gradient of the function f, and this is a vector which components are the derivative of x with respect to the first variable, and of course we should compute the gradient in some point, okay, but we can write without computing exactly in a point. We can compute the gradient and then compute a function. This is the gradient of the function f of x. The vector will have as many components as many derivatives, first partial derivatives there are. That means the number of the variable. This is the gradient. Gradient of f. Of course, if we have a function of more variables, the gradient will have more components. Let's compute the second derivative, because you already done the second partial derivative, and then we try to do as many exercises as possible so that you have more exercises to do. So what is the second derivatives? Okay, the second derivatives are the derivatives of the components of the gradient. That means that we will have two kinds of derivatives of the first derivative with respect to x. So that means we will have the z squared over dx squared. That means that is the derivative with respect to x one more time. So that means that we compute the first derivative and then we derive with respect to x. Or this one, that means that we compute the derivative with respect to x, this first one, and then derive this one. I'm sorry, I wrote z, but z doesn't belong there because we have already our argument of the derivative of this one with respect to y. Okay, so we have as many derivatives as many variables there are. So, what is this? The first one will be the derivative of 2x with respect to x. That means 2. And the derivative of 2x with respect to y is 0. The same kind of computation can be done by considering the two second partial derivatives with respect to x and y of the first partial derivatives. So these are the second partial derivatives with respect to y squared. That means that is, first of all, we have to take this derivative that we already computed and then derive again with respect to y. Then, I'm sorry, I didn't write square, but it belongs to this form with right y and then x. That means that we compute the derivative with respect to y and then we derive with respect to x. So, the first one is again the derivative of e to the power to y. That means 1 more 2 that belongs to the computation as a factor. 2 times 2 is 4. 4 multiplied by e to the yx. The second case is a derivative with respect to x of something that hasn't x inside. That means that we can consider everything as a constant and the derivative will be 0. So these are the partial derivatives. Of course, we have to compute. I think you already computed the Hessian. No, I forgot. You didn't compute the Hessian matrix. Okay, no problem. You will have a matrix that has columns and rows that are the second partial derivatives of the function. Okay, so let's do another example. This time we take a function where everything is mixed, a product function, x to the third multiplied by e to y squared. Okay. Okay. So, what are the partial derivatives? Partial derivatives are, of course, the. Okay, we could write df or dz. It is the same. So we use both. So, okay, what is the derivative with respect to x? Every time you have a product, if you want to compute the derivative, you should compute the sum of two pieces that are the derivative of the first one times the second one plus the derivative of the second one times the first one. But these two pieces are one something that depends only on x, and the other one depends only on the variable y. So it is easier, because if you have this product, you can consider, I will write it down, okay, you can consider, okay, in this case, this term as a constant, Okay. So that means that you should derive 3x cube, this is 3x square, and let the other factor remain the same. This time is not a sum anymore, but it is a product. So that means that if you had, for example, 5x cube, 5 is a constant, and the derivative will be 3x square. What is the partial derivative with respect to y? So we should consider the same, because in this case we have x cubed that could be seen as a constant. So we multiplied x cubed times the derivative of this exponential function. This derivative, we can write maybe the derivative there. What is this? As you know, the argument of the exponential function is its exponent. That means that you have to derive and rewrite as it is the exponential function, and multiplying by the derivative of its argument. That means that you will have e to the y squared times 2y. This is the derivative. Okay? So x cubed times 2y. I always prefer to write everything in front and then the exponential to the right, because it is easy to make mistake if we have something after the exponential function. So, and I'm sorry. Now we will compute the second partial derivatives. So, what are the second partial derivatives? Let's write. So, we have, with respect to x twice, that means with derive with respect to x. All the rest can be seen as something that is a constant. So you will have only the derivative of x squared multiplied by everything else. That means in this case we can consider this piece, and the derivative will be 2x, okay, and then we'll write 2x times everything else. 3 e to the power of y squared. So we can compute the result of 2 by 3, 6x e y squared. Okay, what is the derivative with respect to y and x. That means, first of all, we take the derivative with respect to x and then we derive with respect to y. In this case, we have something that is only that is depending on y. So we have to derive e to the y square with respect to y. So I will take another color. So that means we can take 2y e y square. This is this derivative, y e y square. Okay. And then rewrite everything else that it can be seen as a constant, 3x squared times 3x squared. So 2 times 3 is 6. 6x squared y e y squared. Okay, and these are the two partial derivatives with respect to x. Let's compute the other partial derivatives. So,
excuse me, Professor.
Yes.
I have a question.
Yes.
I
please.
didn't get why the one in yellow is it like that. The partial derivative of that one.
This one that we already computed above.
Yes, the part that you wrote in kind of yellow.
Yeah.
Okay, so it's 2. Yeah.
2y times e y square. 2y square. You didn't get why this partial derivatives why this derivative is computed?
Yes, how we get to the result.
Okay. So I will explain you with another example, but I can put this through. So transparent. Okay. Okay. Maybe I can use a little place there. So when you derive a function of a function, let's say a composition of function, this one, okay, if you compute the derivative of the composition, that means that you should derive the function outside, letting the argument as it is, and then multiplying by the derivative of what is inside. This is the rule. I'll explain you with some example. Take for example a power. So let's say what is outside is a power of something like this. Okay. So what does it mean? That you are applying the fifth power to a function g of x and not only x. Okay? As you know, if you compute the derivative of the fifth power of x, you will have this form. The exponent times x to the power of 4. This is 5 minus 1. And this is a known rule that you have. Okay. That means if you don't have x as an argument of this power, but you have a whole function, you should rewrite the computation as it is. For instance, you take what is inside as it is, 3x, and you will raise to the power of 5 minus 1, that is 4. And this is the derivative of what exactly outside, because to raise by the power of 5 to the power of 5 means take the function g of f and then compute the derivative. But you have to multiply in order to apply in the right way the right form of the computation. You have to multiply by g prime, the derivative of the function that you have inside. That is, g prime is the derivative of this polynomial that will be 2x plus 3. So you have to put inside your computation this part. That very often this part is many people forget this part, but it is very important. So to do another example, let's say and let's return to our function. That means the exponential function. Okay, so what is this computation? It is you remember that the exponent of the exponential function is the argument of the exponential function. That means that if you want to compute the derivative of this one, this is f of g of x. Okay, f is applying the exponential function to its argument, that is its exponent. Okay, this is the same structure as the other slide. Then you should compute the derivative of the exponential function. That means it is again e to the power of the function g, that is the argument as it is. But then you have to multiply by the derivative of the function g. In this case, in this specific case, the function g was y square. So we have to multiply by the derivative of y square, that is 2y. This is why we compute in this way the derivatives. So you should not forget what is the derivative of the argument of the exponential function. I hope that is clear now.
Okay, yes, thank you really much.
Okay, you're welcome. Okay, so let's go on with the computation of the other partial derivatives. We have the f square over dy square. So we have to compute. Now we have more to compute, because x to the third can be seen as a constant, something that is a multiplicative factor in front of the rest of the function. But this function has two pieces, two terms that depend on y. So you have to apply the rule for the computation of the derivative of a product. Okay, that is what I was mentioning before. Plus f of x times g prime. Okay, that is the rule that we will apply. I will maybe in green. Yes. So this is the rule. So we will write x cube, and then we should apply this rule. So let's write it in green. Okay, the derivative of 2y is 2. And we have to multiply by the exponential function as it is. And this is the first piece. Plus, we have to take 2y as it is and multiply by the derivative of e to the power of y squared that we already computed. I will use another column, maybe there's more. So this time, this is 2y e y squared again. Okay? So the meaning is to use this second formula. This is our g. Okay, this is our g. This is this one. So we do a couple of further computations in order to write it as compact as possible. So we can write x cubed, of course. We have a 2 factor that we can put outside. Okay, because we have 2 there and there. We don't need to multiply 2 by 2 with 4 because it's better to take out everything is the same factor. Then we have x cubed. Then we have e to the power of y squared. And then we write what remains inside. Inside we have 1, because every factor we've taken out in the first term, let 1 remain. And in the second one we have one more time 2, and then y squared. Then nothing more. I think it is everything. Okay. Why it is important to write all the derivatives this way? It is important because normally we should compute the derivatives, first of all, in some points, or maybe if they are positive or negative. So in this case, everything inside this parenthesis is positive, for instance, because we have a square of y, 1 plus 2 times a square. Is everything positive? E to the y square, e is always positive. The sign of this second partial derivative depends only on x cubed. So it will be positive when x is positive, it will be negative if x is negative. It will be 0 when x is 0, because everything else, exponential, number 2, the parenthesis 1 plus something, cannot be 0. Okay? Okay, so let's compute the other one. Take the derivative with respect to y, and we derive with respect to x. So what is this? We have to take again this one, but this time is easier because the derivative with respect to x will be computed only by considering x cubed depending on the variable x, and all the rest will be something that is considered as a constant. So that means we have 3x squared and everything else as it is, 2y e y squared. And if we rewrite by multiplying 3 by 2, we obtain 6x squared y e to y squared. Okay, as you can notice, we have the same expression by exchanging the order of the partial derivative that are mixed. That means these two terms are the same. For instance, this kind of property comes from a theorem that claims if the function is a good function, if the function does satisfy some properties, the mixed second partial derivatives are the same. So, if you want to compute the derivative of x with respect to y of the derivative of f with respect to x, or vice versa, the derivative of with respect to x and then the derivative with respect to y, you only need to compute this derivative one time, because the other one is the same. And this is very easy to compute. So let's do another example with second partial derivatives, and maybe then an exercise with with a power function. Okay, so this time we take a quotient of functions. Let's take this example. Maybe more than one variable, maybe more. Okay. So let's do these two examples. More than one variable, so 3 variables. Partial. Okay, I see that you've done some linear approximation in 2 variables. You can do other examples. Okay, let's do this one. F of x, y, and z equals, let's take this power. I think this is an example of Sid Saiter book, plus y to the third plus z to the fourth, everything to the power of 6. Okay, so how many derivatives should we have? Many. Of course, we have more derivatives, because we have, first of all, we have to derive with respect to x, then to y, and then to z. And maybe these are long. We can compute the first derivatives, then let's switch to another example in order to compute the second partial derivatives. So, what is df over dx? So in this case, we can apply the same rule by the computing of the derivative of something that is a composite function. So everything is inside this parenthesis raised to the power of 6 belongs to the function. And we can see this function as a function of x plus some constant. So in this case, we rewrite the rule 6 times everything that is inside as it is, because it is a composite function, raised to the power of 6 minus 1, that is 5, and then we should multiply by something that is the derivative of the argument. What is the derivative of the argument with respect to x? We have to derive only what is that is depending on x. Everything else it can be considered as a constant, and the derivative of a constant is 0. So that is 12x multiplied by everything is inside this parenthesis plus z to the fourth. Okay, so let's compute the derivative with respect to y. The derivative with respect to y, again, it will be the same, because we have to derive, first of all, what is outside. This is a function of a composition of function, but then we have to multiply by the derivative with respect to y of the argument, that is what is inside the parentheses. So we have this time 3y squared, and everything else derived will be 0, because everything else is considered as a constant. So we obtain 18y squared multiplied by x squared plus y to the third plus z to the fourth power. Okay, let's compute the derivative with respect to z, and this is the very same as before, but what we have to consider is this time the derivative with respect to z, 4z to the power of 3. That is 24z cubed multiplied by this parenthesis plus z 4 to the power of 5. What are the second partial derivatives? We should derive with respect to every variable all three partial derivatives. That is, we have 9 partial derivatives. We have d of f squared. So we take dx and we derive with respect to y, with respect to x again, and we can write square, and we derive with respect to z after we computed the first partial derivatives. That is for every of this kind of function. Because it is a little longer, I would compute another partial derivatives of a function that maybe can be useful, because there is again the exponential function, so we can practice a little bit. So let's take another slide. I didn't watch if there were some questions, but I think there aren't. Okay. Okay, so let's take this one. F of x, y, and z equals e raised to x times y times z. This is a product, okay? And as you know, it is a function of all three variables. If you consider the more variables, you have to derive everything with respect to any variable that you have. Let's take okay. I was watching some other exercise, but I think this one is good. Okay. Okay, so let's compute all derivatives. Okay. df over dx. Okay, this is a whole function that has as an argument x multiplied by something. So what are we doing? We take the derivative of the whole function as it is, because this is an exponential function. And then we multiply it by the derivative of xyz. xyz is a product. That means it is, with respect to x, as a product of x times something that is a constant. That means the result will be y times z. Okay, maybe I write it yz prime. It is yz with respect to x. With respect to x. Okay, so we can write maybe better this way. I put y and z in front of the function, and then we compute the other derivatives of the function. So the very same computation, because e to the power of xyz will be the same, and then we have to derive the argument, so the exponent xyz with respect to y. So the derivative of y is 1, and then we are left with x and z. This is the same computation. Then we compute the f with respect to z, and as you can imagine, it will be xy times e to the x, y, z. And so we have compute. Yes.
Excuse me.
Please?
In this case, e to the power of x, y, z, we could consider again the form of e to the power of g of x, where x, y, z is g of x. Okay, thank you.
Yes, x, y, z is a product that it is considered as the argument of the exponential function. Of course, maybe I can do another example that comes in mind, because if you have, for instance, let's say something like x squared times logarithm of x. Okay, this example has nothing to do with our more variable function, but it is important because if you have this form and every piece, every factor of the product depends on x, if you consider this one and you want to compute the derivative will be e to the power of the whole function. Let's say this is g of x, okay? Okay, but then you should multiply by the derivative of g of x, okay? In the first case, you had 3 variables, and every time you had to derive with respect to only one variable. This time, you have to derive with respect to x, and you have 2 factors that depend on x. That means that the derivative of this g of x will be the same as the computation of the derivative of a product, because it will be the derivative of the first one, so of x squared, that is 2x, times the second one as it is, plus the first term x squared times the derivative of logarithm of x, that is 1 over x. Then it is complete. I hope maybe this example was helpful. In the first case with our function of more variables, this product was considered every time with respect to only one variable. But in case we have a product that was depending on the same variable, two or more terms, then we should have used the other rule for the derivative of a product. So let's compute the second derivatives. Okay, let's take all the derivatives with respect to x and compute. Okay, this one has the same form as before because x is only in the exponent, so it is again the whole function, and then you have to derive with respect to x the whole exponent. That means you rewrite y and z, and you write the derivative of x, y, and z, that is at e to the x, y, and z itself multiplied by y, z. So you will have y square, z square, x, y, z. Then the second derivative of x with respect to x and then to y will be again the first one, but this time you have to consider that we have a y in the front of the function. So you have to compute a product. Z can be considered as a constant, okay, as a multiplicative constant. So you have to take maybe y times z e to x, y, z, and every time you have to derive, you should take in account that you are deriving this and this with respect to y, okay? So then you will have the derivative of y, that is 1, with respect to everything else as it is, plus y as it is times the derivative of this second piece, and this one will be everything as it is multiplied by the derivative with respect to y, that is x, z. Okay, let's put it everything together. So we have z e to x, y, z, that is everything in the first term, so we have 1, plus this piece is already outside the parentheses, so we have x, y, z. X, y, z. Okay. Now we can compute the second derivative with respect to x and then to z. So we take the first derivative again with respect to x, and then we derive with respect to z. In this case, the computation is very similar to the previous one because z appears in front of the product, and we can consider the product, for instance, let's say yz as a product times e to xyz. In this case, the only variable that we should consider is z. So we can see the first factor of the product as some number, some constant y times z, and the second one as the exponential function of some constant xy times z. Okay. So let's write it as the derivative of the first term is 1 times y, and we multiply by e to the xyz, and then we have to sum everything as it is in the first place times the derivative of e to xyz. That is, again, xy e to xyz. Now we can take out as a factor everything that these terms have in common. And then rewrite x, y, z. As you can see, it is the same piece. X, y, z. Only we have y and z that are different. I'm sorry, maybe it was a little fast. Okay. Of course, we can compute every other derivative with respect to the other first partial derivatives. They will appear the very same, because as you can see, the form of these derivatives remains the same. So if you have to differentiate, you can compute in the same way. I would exercise. I will do more exercises, maybe by computing maybe linear approximation and tangent plane to variable function. So we can compute some example, and we can substitute some values. So let's take an example. I was wondering if you have already done a linear approximation of two variables. I think so. Yes, I think, yes. Let's switch to another slide. So, when we have to compute the linear approximation of some function, let's take this function Okay. This function, I think this is another example from the book. F of x and y is x y cube minus 2x cube, and we should write down the linear approximation of the function f and near the point P of coordinates x0, y0 equals 2, 3. That means we should compute the form that can have the function near this point. So we have to compute a very easy polynomial that has only the first power of our variables, not this power. It could be everything, exponents, every kind of function. What is the formula for this linear approximation? We use this one. I think it is the same that you have seen at your lecture. So we write in this way. It is something like, and then the first is the function computed by the point P. So f of x0 and y0 plus it should be a product, a scalar product, but we will write this way. The first derivative with respect to x computed in x0, y0 times x minus x0 plus the first derivative with respect to y, again computed in x0, y0 times y minus y0. Okay, fine. This is, I think, the formula that you have, and we could find a value. Again, we can yes, we can find a value. Okay, let's write the function. What should we compute? We can compute f of x0 and y0, that is the function computed in at the point where x equals 2 and y equals 3. So it is f of 2 and 3. That means 2 times 3 cube minus twice x cubed, that is 2. Okay, so this is 2 times 27 minus 2 times, so I could rewrite without performing the computation, because it is 2 times 27 minus 2 times 8. So 27 minus 8 is 19. 2 times 19 is 38. And then we compute the first derivative with respect to x and with respect to y. So first one is the derivative of x, it is 1 times everything remains in this first term, y third, minus 6x squared. And then we compute the derivative with respect to y, that is 3xy squared minus, but there is nothing depending on y in the second term, that means that is 0. And then we compute the value of these two partial derivatives at the point 2, 3. The f of 2, 3 computed. It is 3 cubed minus 6 times x squared 2 squared. So it is 27 minus 24. That is 3. The second one, computed in 2, 3, is 3 times x, that is right, times 2, times 3 square. This 3 times 3 square is 27, times 2 is 54. Okay. So we are done. We can compute the linear approximation of this function near the point 2, 3. So f of x and y is 38 plus 3 times x minus 2 plus 54 times y minus 3. Okay, if we solve, we can compute, so it is 38 plus 3x minus 6 plus 54y minus 162. That is equal 3x plus 54y. And then we have to sum up. It is 32. It is minus 130. This is the linear approximation. But if we want an approximate value of the function near the point 2, 3, and we have to compute, for instance, an approximate value of the function at values that are 2.01, 2.98. As you can see, this is very close to 2, the x, and the y is very close to 3. Okay, that means that we can find an approximate value of the function only by using the formula. That means we can use, instead of x and y, these two values. We have two ways to do that. We already computed the linear approximation, and we had a formula for which we can substitute the values of x and y. Or we can rewrite the first part of the formula by taking into account that 2.01 minus 2, it's 0.01. That means 1/100th. And 2.98 minus 3 is very small but negative. It is minus 2.02. So if we compute this, it is the same, okay? It is the very same, but we already substituted the very small values. We have only to compute 3 times 0.01 and 54 times minus 0.02. Okay, this is easier to compute, and that is this is 0.03, the second term. (0.03), and the third term, it is 54 times 2, but divided by 100. This is 108, and divided by 100 is 1.08. So it is very easy to perform this computation. 38 minus 1 is 37. 37 minus 0.8 is 36.92, and this is 36.92 plus 3. So the approximate value of this function at these two values, this point, with the values 201 and 298, can be given by this formula. Wait a minute. Okay. If you compute this function, if you take your calculator and you compute the very value of the function with your calculator, so I can do it right now, and you take this whole expression x y square minus 2x third, and you substitute the two values, you will be very close. You will be very, very close. Okay. Let's do another computation. I hope this
Professor.
will... Yes, yes. Please.
Excuse me, but the value to 0.01 and 2.98
It's
are...
some value.
Okay.
It's given. It's something
okay.
that is made up that is very near the point 2,3.
Okay, but it's given by the exercise?
Yes, yes, of course.
Okay, thank you.
Yes, yes. Of course, I could have given you, I don't know, something like this, 1.98, that was close to 2, and 3.01. It would have been the same because it was another point for which the values of x and y were close to the values 2 and 3 that we were considering by our linear approximation. That is the reason. That normally it is the text of the problem that will give you some values in order to compute the linear approximation or some other kinds of computation, or maybe if you are asked to compute a linear approximation near the point, maybe you can take as an example this kind of computation, because you have to check for a value that is very close to the values of x and y of your point P, that has the coordinates 2 and 3. Okay, so let's do some. Yes, please. Some other question?
No, I'm also saying
okay.
say thanks.
Okay, you're welcome. No problem. I wanted to compute. I forgot, but maybe we can do now. A partial derivatives of a quotient. I'm not sure if we computed last time. I don't think so, because we had some quotient. Let's see. But we only computed something that was one variable function. Okay, but the formula. So you already have the formula for the quotient. For the derivative of a quotient, but I wanted to use this formula in order to compute the quotient when we are considering a more variable function, and that will be our next example. Maybe I add a frame there before the linear approximation, so we will remain by the same argument, because the partial derivatives, there are some examples in the book. I will take some example like this one. Yes, this one is fine. Okay. So f of x, y, and z, let's take a 3-variable function, is equal x to the 4th over yz. Okay, so in this case we have 3-variable function, and we compute the partial derivatives. As you know, the formula for the derivative of a quotient you have in the previous slide use whole function. Take from the whole function the denominator square, and then formula that is very close to the formula for the product, but it has a minus between the two terms. So let's compute the first partial derivative with respect to x. Okay, first of all, we have to apply the formula as it is. That means the denominator square, and then on the numerator we have to write everything that corresponds to the formula we had. That means the derivative of the first of the numerator, 4x to the 3rd, times the denominator as it is, minus the derivative of the denominator, but with respect to x. That means it is 0 times the numerator. That means we remain with only one term over the fraction, and this will remain the same. Then we derive with respect to y. So, as before, we will have the square of the denominator. And then we shall derive everything is over with respect to y, that is 0. I write 0 times yz minus the derivative of the denominator, and this time the derivative of the denominator is 1 times z times everything is over the fraction as it is. That means this is a negative sign before the fraction, x to the 4th yz square. Okay, the third with respect to z have the same denominator. This time the first term will be 0 as the previous one, and the second term will be minus, and this time the derivative of the denominator with respect to z is y times 1 minus y times the numerator. So this is the first partial derivatives with respect to z. Okay, as you can see, you can of course take some factor out. That means you can
Sorry. It's not,
yes, please.
It's not y in yx.
Yes.
Oh, thanks. Thank you.
I copied what was in the previous one, but it is correct. It is y, of course, because it was y before. Yes, thank you. I could rewrite everything as by computing, by simplifying, of course, some powers, because we have y and z, for instance, over the fraction. You can simplify y and z, and the two, maybe we can do it in one step, and then it remains this one. Of course, if you have to compute some value of these partial derivatives, it is easier to simplify something that you already have. In the second case, you have 1 power of z, and you can simplify 1 power of z with 1 power of z under the fraction, so we will remain with this one. And in the third case, you will have x to the 4th divided by, and you can simplify y, and you are left with z square. Of course, if you want to compute the second partial derivatives, we have 3 variables. You have to derive with respect to all 3 variables every partial derivatives. So you will have 3 derivatives for all for every first partial derivative. But the meaning of the computation, the way in which we computed these partial derivatives are the same that we should use for the second partial derivatives. For instance, let's compute one of them. For instance, this one. Let's compute with respect to x twice. Okay, so we have to take this one and then derive with respect to x. That means we take the square of y and z that we have on the denominator, and then we multiply by the derivative of 4x to the third, and in this case it has a value 12, because it's 3 times 4 multiplied by x squared, times the denominator as it is, y and z, minus something that is 0, because I should derive with respect to x the product y and z that I can consider as a constant. So that is what remains. If we derive with respect to y, and maybe the other derivatives that are left, I'm sorry, this is not the correct. This is the derivative with respect to y of the derivative with respect to x. You have to write again the denominator as it is, and then you have to derive the numerator, but it is 0, so it doesn't matter, minus the derivative of the denominator with respect to y, that is z, and then multiplying by the numerator, 4x to the third. Okay, so it is minus 4x third z divided by y z square, but maybe you can simplify 1 power of z and rewrite instead of z square only 1 z, and so on. Okay, so I think it was important to compute again some quotient, because you have to differentiate every time. Every time you have to differentiate what it is considered as a function of a function of own variables. You can consider as a function the variable with respect you are deriving, and the other only constants. Okay, so I think it is enough. I'm not sure. You already have some exercises that the professor gave you, but I will ask for other exercises. I think you can find in this book that the professor gave you. The name of the book, one is the Sid Saeter, and you will have you will find the 5th edition of I will write Sid. This one. It's my name that you already have. I'm sure that you already have. And maybe I will speak again with the professor, and depending on what you will doing at the end of this week, we can perform some exercises for the next week. I'm not sure of the day. I think next Tuesday. I let you know which day. I think maybe now we can stop the recording, and then you will have this recording on your chat. Okay, so I think this is everything for today, and we will meet next week. I let you know. About the name of the book. Yes, I thought you had the name, but I will I will find. Should be this one. Essential. This will be the name. Mathematics. For economic analysis. It should be analysis. The name of the book. Yes, this is what I was thinking. This is the book. Yes. Okay. So I will share the PDF. I think I can put the slides all together in one, and then I will give you the PDF of the 2 lessons that we made. Okay, so we will meet next week. I wish you a good day, and until next time, goodbye. Bye to everyone. Bye-bye.
Thank you. Bye.
You're welcome. Bye-bye. Bye.